Thanks a lot. This is a great honor to be here. And I'll be happy to talk about the forwarding plane today. So I called it the old new frontier because obviously we've been using forwarding plane or data plane. Every networking device has forwarding plane. So that's why it's old. But at the same time, it's becoming very hot and very exciting in this field, especially these days. So that's why I wanted to talk about this. And this is SDN. So I felt like, defining this what SDN is because, it's always good to start with some firm definitions. And SOSR and UNF is one of the main, organizations driving this thing. So I felt like finding this definition there. And then their definition is reasonable, and it's probably good enough for people like us. But at the same time, I am sort of a firm believer of easy explanation on any topic that I talk about. So I just wanted to come up with a better and easier definition of SDN, my version, right? And then ideally at the level for college freshmen, because according to Mr. Feynman, if you're not able to explain anything, irrespective of how hard it is, at the level for college graduates, or college freshmen, then you're not really understanding it. So I wanted to at least give it a try. So here's my version. Making programming networks as easy as programming computers. And I came up with this one because if you're, a college freshman these days, you should definitely know about what programming computer means. And then you should definitely be taking courses on those kind of things, especially these days. So I just wanted to give this kind of definition. Then, of course, a lot of natural questions follow, okay? Why should you program a network? I can understand why I have to program computers, but why should I program network? And of course, not everybody has network. It's not like phones or your laptop. But as long as you have your own network, you have desires to improve your network. Let's call it your beautiful ideas. And then you want to realize those beautiful ideas, and ideally on your own, because we all know that when the users of some device are the programmers at the same time, a lot of great things can happen very quickly. The second natural question that can happen is, okay, good, then what are those beautiful ideas? I mean, in networking especially, what are those cool ideas? And of course, there could be a lot of improvements on networking or packet forwarding itself, but are we actually observing something more than just packet forwarding here? Any impactful or intriguing, beyond just packet forwarding? Are there such ideas here? The third question, okay, good. No, I can understand why we should program the network, what kind of things we may want to do, but why couldn't we do this before, earlier, like 20 years ago, 30 years ago, right? So are we actually observing some fundamental technical shift at this point in time that is happening? So these are the big questions that came up in my mind, and I wanted to talk about some of these, maybe not exactly in this order in this talk today. Okay, so this is the pre-SDN state of the network industry. Right? You have your own network, your big enterprise organizations or online service providers, and then you have some ideas, your beautiful idea. Let's call it just a feature. You say, hey, I want this feature. You go to network equipment vendor, and then they have their own engineering division who is comprised of software team and ASIC team, and then these companies used to build a sort of purpose-built monolithic systems, and these were sort of good engineering achievements, or maybe depending on the view, you could call them good engineering artifacts, but they were not necessarily built with clear and clean architectural principles behind it. But anyway, they met the performance, they met the demands, and oftentimes to deliver this new feature, they had to introduce new feature even at the hardware level. So they all said that, okay, good, now I understand your requirement, but give me 3 years. Okay? And of course, the answer is just transferred to you. You're the network owner. So you have to wait 3 years and years And then later on, you realize, oh, I could actually use some kludgy way of tweaking these things on my own. So the problem is almost half solved. I'm okay now. I'm now moving on. Or after 3 years, you realize, oh, I received this feature, but I have to upgrade my whole system, my whole network with these new functional systems. But also at the same time, this is not as great as I wish it could be, because they're not just working only for you, they're working for many other people, and then when they merge these features, something happens, some unexpected fusion happens. So compared to the other industry or sub-industries in IT field, this is very, very unnatural. We all know this because to researchers and developers like us, programming is just a commonplace. We program CPUs, obviously, we program smartphones, we program GPUs, we program even TPUs these days. Right? So why can we do this? And also, what are we actually losing by not being able to program my networks? So in these other industries, we use programming or programs every phase, not just implementation, but for verification, testing, deploying, even maintenance. We have a good theory, we have good disciplines, we have great best practices to build and deliver things and manage these things using programs. We're not benefiting from any of this in the networking industry. They have extremely fast iteration and differentiation. We also don't have these kind of things in networking. We didn't have this kind of thing well enough. And then by programming the target, you always own your own idea. It becomes yours, right? We didn't have that benefit either in networking. And so therefore, we didn't have a sustainable ecosystem which can just keep adding more things, beautiful things. So I believe SDN really started with this fundamental question. Maybe that was about, 10, 15 years ago. Can we replicate this kind of healthy and sustainable ecosystem in networking? So that was the fundamental trigger. And then I believe what all the SDN pioneers had realized at that time was something like this. Okay, I'm a network owner. I have network equipment. I have to go to network equipment vendor to share my feature ideas. But in reality, what is happening is this one. If my feature can be realized in software, they also can just give this back in weeks or months. But if I had to introduce something that depends on the hardware, then it becomes years. Okay? So at the end of the day, I got this answer years because these two were tightly coupled. Software taking care of the control plane, hardware taking care of the data plane or forwarding plane. But if I can decouple these two things, then at least I can achieve this agility and flexibility, at least on the upper half of this diagram, right? So that's how SDN started and then started to unfold. So to some network owners, like enterprises and organizations, it probably have become something like this. So on the lower half, you still have to wait years. Right? So that's very hard to change. But at least on the upper half, you're now working with network control plane vendors, such as VMware, or a lot of other companies are delivering now network control plane solutions. And then their software teams can deliver new features or bug fixes in weeks and months, right? So you at least take advantage of those things. And then to let these two planes communicate more formally, you introduce a lot of abstraction interfaces, such as OpenFlow. We started with OpenFlow, and then recently there are other types of abstractions, such as SCI or P4 runtime is actually the new abstraction that P4 community is actually pushing forward to enable flexible and language-driven interface between these two planes. Okay, good. At the same time, you're a network owner, and then you actually have a big and powerful development muscles, like your online service providers. Then you actually created your own software team doing control plane within your organizations, and then you're now enjoying this benefit even in days and weeks, right? And also, sometimes for technical and business reasons, you open source this project, and then you actually work with external open source contributors on the control plane as well. So this is what has happened recently. But as we can easily see, this upper half of this diagram, has become now an innovation-rich programmable layer. But what about this lower half? Is this still going to remain as innovation-deprived, ossified layer? Actually, we need to look at this lower half a little more carefully because it's not just simple to say, okay, this layer is not changing at all. At least there has been some interesting changes that is happening. So let's look at this lower half a little more carefully. So the lower half, the biggest problem of this lower half is that you cannot violate the laws of physics. Right? You have bits and power consumptions and all those extremely hard electrical engineering problems, or sometimes even physical problems. So that dictates the actual the growth and the upper envelope of this the growth of this lower half. So I'm just plotting here the fastest switching chips that are released at this time frame. So this is a time series. And then on the y-axis, you see the speed of the chip in gigabits per second. And this is a log scale. So we're actually growing exponentially. I'm just plotting this with log scale chart. And so right now, this is 6.4 terabps. And then this is the fastest CPU or the fastest server NIC at that point in time, the corresponding time. So as you can see, there is significant gap here. But at the same time, this can also mean opportunity here because at least this lower half, if your performance goal is below this curve, this red curve, it means that you can actually use the CPU's flexibility. So that means you can actually introduce software switches and hypervisor switches and then enjoy your benefits. And definitely if you look at one server, like virtual switches or server NICs, you can take advantage of this level of flexibility. That's totally fine. That fits within your budget. So that's why a lot of innovations are happening at the server host side. But what about this other zone here, right? Is this going to remain as an unaccommodating performance-dominated zone as it is? Actually, it turns out that a lot of things are happening within this gap, which is not trivial. ADX is like 2 orders of magnitude. On the lower half, or from the bottom, we're observing the introduction of what we call smart NICs. There are FPGA-based smart NICs or some ARM core CPU or NPU core-like smart NICs. They can handle maybe 2x, 2.5x than just vanilla CPUs. So from the bottom, you're actually observing some programmability actually creeping into this sort of zone or dead zone. And then at the same time, from the top, the chip itself, the fastest chip, is also becoming flexible. Okay? So today I'm going to mostly talk about this attack that is happening from the top, from the switch chip side, because that's mainly what I've been working on for the past few years. Okay? So the conventional wisdom here in the networking industry, especially in the hardware industry, was that you can probably build programmable switches, but it's going to be damn expensive and damn power hungry. But we now know that this is not true, and I'm going to tell you why. Okay? And here is the evidence that at least Barefoot has delivered, and then we know that some other companies are also working on this, and then a little lower speed range, like 3.2 terabps. At least there's 1 or 2 other companies who have delivered similar kind of products. Okay, so this is the world's fastest and most programmable switching chip today, and there's no power cost penalty here compared to the fixed function switching chips. And then we're calling this PISA architecture, or protocol independent switch architecture. Okay, so and this is the way I view PISA in the big scheme of things in computing industry. So in the really old days, like if you know what happened in the 60s, they actually built application-specific CPUs, right? Of course, it is ridiculous these days, but I just wanted to set the starting point here. About 20 years ago, GPGPUs arrived, and then the industry entirely changed. Nobody's building fixed function GPUs anymore because that GPGPU has become the fastest and fully flexible programmable platform for the GPU industry. DSP industry, the same happened. Nobody's building fixed function DSPs anymore. Machine learning, it is happening right now. TPUs or similar kinds of chips are being developed by many people. And what about networking? Okay. So the common pattern here is that for each specific industry, after maybe spending 10 or 20 years, people realize that, oh, there could be some common abstraction that I can deliver for this particular industry. Let's build the target hardware that handle these abstractions, common abstractions very well, and then let the compiler, translate this complicated application logic to the abstraction interfaces, okay, for the abstraction interfaces. So that pattern repeats, and then what is the language for domain-specific language for networking or network forwarding plane description? P4, I believe, is one such an answer. And then the target is PISA, okay? So from now on, PISA will have the same speed, power, and cost as fixed function chips. But we need to understand why. Why is it happening just now? Okay. So these are just a chip layout of some of the widely used solutions from many different vendors. But let's look at the chip area or the layout or real estate layout of these chips internally on the die. So the biggest portion of the chip area is actually spent these days to build this thing called serial I/O or SerDes. Essentially, this is converting serial signals coming into the chip into the parallel signals, and then when you need to ship the packet out, you have to do the inverse of that. That's called serializer, deserializer. It works at very high speed clock, like today maybe 26 or 28, and then next generation 56, and then the next generation 128 gigahertz. So this is actually using a completely different clock cycle than the rest of the chip. A lot of analog digital mix. Very difficult logic to develop. So this takes about 20 to 30%. Actually, these days more like 30% of the chip area. And this is Clip. This is Tomahawk. This is Tofino. So it's actually growing. Every new generation, the area consumed by SerDes is actually growing, trending up. So why is it so? Why is it growing up? So this is why. So every time we go from chip generation K to K plus 1, so K we would say maybe 32 nanosecond solution, and this is a 16 nanosecond solution, K plus 2, say 7 nanosecond solution from some manufacturers. Every time we jump from generation K to the next one, Moore's law kicks in, or the technology node, processing node benefits kicks in, so you can make your gates smaller and smaller, you can pack more gates, but at the same time, your market, your consumers are asking for more speed. So usually you have to double the speed. So you have to introduce higher clock speed, more SerDes, and so on. So therefore, at the end of the day, you end up spending roughly the same or even more physical space when you go from generation K to K plus 1. So the same happens. So that's why the area spent by SerDes actually does not go up. Okay, let's look at the next big portion, which I called here packet processing, but it's actually, you can subdivide this into two portions. Roughly, one half of this packet processing logic is the actual memory, SRAM, or TCAM, that is needed for table lookups, basically match resources. The other half used to be sort of packet processing logic itself, where you actually implement IP or MPLS or multicast and so on. And then the other 20% is the actual switching logic, queues and buffers, where basically a large, very fast multi-port shared memory, right? So let's look at this memory and packet buffer, because these two are similar. These are essentially just large but very capable SRAM, or in CPU analogy, this is a really big, gigantic L1 cache. Okay. So the memory consumption, again, when you go from K to generation K plus 1, Moore's law kicks in, but unfortunately you have to double the storage. Everybody says, I need more larger routing table, I need more buffer, and so on. Right? So this doesn't go up, go down. Okay. Now, what about this other portion, logic portion? Okay, so this portion dictates whether the chip is actually fixed function or programmable. If it's fixed, you actually realize particular protocols in VHDL or Verilog at this level. If it's programmable, I'll show you how we build this kind of chips. Okay, so this portion, more so kicks in, but the number of new data plane protocols you have to introduce at each generation is not increasing like that crazy, right? We've been using IPv4 for the past 30 years. IPv6 was invented like 20 years, right? So this increase is not that drastic. That's why it keeps coming down and down at every generation. And right now, this has become much smaller. So this maybe about 10 years ago, this was about 25%. And then now it got smaller and smaller. Right now, it's less than 15%, or maybe in our next generation chip, it'll be definitely less than 10%. So what this means is that programmability may add a little bit of penalty here. This logic itself increases, say, by a few percent, but this logic itself has become significantly smaller than it used to be. Therefore, the cost of adding this programmability is now marginal. It's economically and power-wise viable. Okay, so this is what is happening in the industry. Therefore, as you can see, the more programmable the chip is, the more sort of visually pleasing it is. Right? It's homogeneous, and it looks like some modern I don't know, abstract expressionism something, right? It's easier to see at least, and so that's the hallmark of programmability in the chip. Okay, and also because this is so homogeneous and regular, this becomes a good compiler target. Okay, so what is PISA then? At least I hope I explained why this is happening now, but I just wanted to spend a few more slides to explain how this actually works. So, like any other packet processing machine, it starts with parser, but in PISA machine, this parser is programmable, and then there are multiple physical stages of packet processing units. And then in each physical stage, you have multiple match action units, MAUs. So the unique thing about here is that each physical stage is exactly the same as all the other physical stages. And each MAU is also exactly identical to all the other MAUs. There is no custom special purpose stage or MAUs here at all. And if you have data dependencies, right, read after write or write after write and so on, then you have to address them by laying them out, laying your logic in sequence here. So that's why we need multiple stages. And within each stage, if you have multiple MAU actions that can be executed in parallel, you can do them in parallel because we have multiple of them. Okay. So when a packet arrives, you essentially parse them. Parsing is essentially just reading header and header fields and then sort of slicing them and then packing them into the containers. You can think of it as registers, data registers in CPU world. So we call these registers packet header vector, PHVs. And then PHVs are used as an input to these match action units. And then when you do the lookup, you get no match or one match, and then you execute a corresponding action through this ALU, and then it generates it changes the contents of the PHVs or add PHVs or remove PHVs and so on. And this next set of PHVs go to the same process in the next stage, and this repeats. And then when it arrives at the last stage, it gets sort of reassembled, which we call deparsing, and then it's sent out as a packet, as a new packet. Okay. So, of course, to build a really useful switching system, we need to make this a switching system. So we have to add a shared memory buffer in the middle. So you have ingress match action logic and egress match action logic, and this becomes more like a switch now. And so ingress means that it's pre-switching stages. Egress means it's post-switching stages. And then to make this more general, we have to dedicate some ports to CPU. so that you can communicate with the control plane. And then you can also add programmable packet generator in front of some pipes or some ports so that you can generate your own events or packets as well. And then for some complicated logic, you can actually do recirculation, meaning that the packets are actually fed back into the ingress again so that you can process some packets multiple times. So that's the very high-level explanation of this PISA machine. And then what is this match logic? Essentially, this is a mix of SRAM and TCAM for lookup and some generic stateful resources that are necessary to build counters, meters, and hash tables, and so on. And then what is this action logic? It's essentially just a simple ALU that can handle standard Boolean and arithmetic operations that are necessary for packet processing. And it also has some special instructions for header modifications and hashing and so on. Okay. So this is essentially a generalization of the RMT paper published at SICOM a few years ago. And the interesting thing, but obvious thing about this machine is that it doesn't do anything until it gets programmed. It doesn't even understand Ethernet header or IP header. So you have to program it to use it. And P4 is the language. And then again, P4 paper was published by a few years ago by a few luminaries in the networking field. P4 language consortium started with that initial proposal and then worked very hard to actually produce sort of production grade P4 language specification and tools as well. So again, this is Apache license-based full open source software. The latest and largest common language that this community has delivered is called P4.16. 16 following the year 2000. It means 2016 in which we finalized this specification. And then it supports various types of devices and targets. It's not just used for high-speed switching. It's used for software switches like OVS, and there are P4 programmable smart NICs and P4 programmable NPU-based middle boxes and so on. Okay. So the goal is enabling a wealth of innovation, and then there is very low barrier to entry, and then multiple working groups are working. So there is language definition working group, machine architecture working group, and then the API working group working on the P4 runtime protocol, and applications working group, and so on. So I just wanted to briefly talk about P4.16 because this is the new common language, and a lot of people have started adopting this language. At the look and feel level, this is almost identical to P4.14 or the original P4 version, but it became a much more real sort of language that can actually please the language specialist as well. So a lot of language people actually joined in this design process, language people and compiler people. So we really scrutinize this language with the eye of the language experts. Okay. So the two main new things, architectural. Basically, we wanted to offer some heterogeneity or embrace some heterogeneity, and so we're essentially talking about two types of heterogeneity. Architectural heterogeneity, meaning that hey, you have this P4 target, it may have, say, 2 pipes internally or 4 pipes. The programmable person here may be limited to some areas, like match action, but maybe switching logic is not entirely programmable. Or parser is not yet programmable, but match action is programmable. So different architectures from different vendors or different solutions or solution base may have different limitations or capabilities in terms of programmability. We wanted to share the same P4 language core so that different use cases, different users can still use the same language to program different types of devices. That's what we call architectural heterogeneity. And functional heterogeneity. Again, some targets may have some complicated logic, like for example, encryption, decryption, or maybe pattern matching against the entire payload, whereas some other targets may not have those things, but instead these things run at 10 terabps, much higher speed. So we just also wanted to accommodate these kind of differences without polluting the language or without regrouping to define new language generations or subversions every time you had to deal with these kind of differences. So that's what we call functional heterogeneity. So P416 now has features to support these two heterogeneity capabilities. We also wanted to improve portability and composability. But to be honest, portability is not that great yet. It has significantly been improved than the previous version, but we are looking for a lot of help from the community, especially application owners or language experts to define better portable solutions here. But at least we have a lot of other supports that modern languages offer, like local namespace, local variables, parameterization, sub-procedure like constructs. So we have at least these kind of things now. And then we also tightened up the language further so that it can be more intuitive. For example, expressions are now allowed, and then execution semantics are not anymore parallel. No software developers understand parallel execution semantics, whereas hardware people find it very natural. We decide to go more friendly to the software people, so we're using sequential semantics and strong types and so on. Okay, so now the question. Now I understand what PISA is and how, at the very high level how it works, and then I know that there is P4 language, but what does a compiler do here? It seems like the compiler works very differently here because the target machine is very different from CPUs or similar kind of machines. So this is one way, this is my attempt of explaining that. So let's look at one particular match action unit. It looks like this if you magnify it. So it has incoming PHBs coming in, and then this is outgoing PHB from that match action unit. And then this match action unit essentially is comprised of a gigantic crossbar because any PHB or any registers can be used as a lookup key for this matching. And then sometimes you use just keys themselves or headers or header fields as they are as lookup keys, but sometimes you have to hash them to use them as lookup key. So you have to have hash generation logic, you have some multiplexers, and then you have the match table built with SRAM or TCAM. And then once you look up the match table, you have a corresponding action, basically instruction. So you have to keep this instruction and the instruction parameters in the separate memory. And then these are now finally fed into the ALU as one set of parameters, and then the other set of parameters are basically these PHBs. Okay? And then the ALU performs the specified action dictated by this match result. And then this basically modifies the PHBs or add PHBs or remove PHBs. So this is the internal logic of MAU. And what the compiler does, when you have your P4 program, the P4 compiler understands the P4 program first. And then what it generates is not a binary code like for CPUs. It doesn't have stack or those kind of things. Right? Instead, what it generates is the configuration of a millions or maybe tens of millions of control registers. So this machine essentially realizes your application through the values and specifications of the control registers. So those control registers essentially dictate the mappings of these PHBs, or these PHBs are used to carry these header fields in this particular physical stage. You have to configure this crossbar this specific way. You have to configure the hash polynomials this way. You have to partition this match table this way. You have to introduce these action codes and action parameters. You have to configure these multiplexers such and such way. So that's the actual binary of your P4 program. Okay, good. So that's the part that I want to talk about regarding P4 and PISA machine. But now let's talk about the applications. So we're all doing this to do something exciting. So what kinds of new and exciting opportunities are arising here? There are many. I mean, of course, people are using this machine and P4 language to improve their networking. So their way of tagging, their new way of encapsulating things, their new way of forwarding packets. For example, high-frequency traders are now parsing their stock exchange protocols called each or something else, a lot of other things, to be able to filter or deliver these packets in a custom way so that they can reduce the latency as much as possible. All those things are happening, but still those are sort of more typical networking, in my opinion. Are there any really crazy and very exciting applications? So I wanted to talk about 2 such applications today. So the poster child use case is telemetry. And why is telemetry so important? Because gray failures and performance debugging is so difficult when you have large network and you're just spending millions, maybe hundreds of millions of dollars every year to be able to just there. Okay? So, and what do I mean by telemetry? So I wanted to define maybe 4 ground truth questions regarding any telemetry technologies. So this is your network, packets are being delivered. Pick any packet in your network, and then you have to ask these 4 key ground questions. Hey, packet, which path did you take? Which specific physical path did you take? Let me know. So you are expecting an answer like this, right? Okay. And second, why did you take that path? More specifically, which rule did you end up being matched? Because that explains why you took path X as opposed to many other available paths. Okay? The third question, how long did you wait? How long did you end up spending at each hub in your network? Okay, so you're expecting an answer like this one. And you can quickly plot these kind of things. Basically, you can build a time series of latency. And then in this kind of switches, if you can ignore, or at least this propagation latency and transmission latency is fixed. So let's talk about the variable latency portion, which is queuing delay. So you can actually plot your queuing latency in time series. And then if you see this kind of big hump, you should be able to explain what's happening here. So the fourth question is, who did you end up sharing the queue with? And in this particular case, for example, there was an aggressor flow, an orange flow, that just happens to be sharing the same queue, output queue at this switch with this green flow. And then that guy actually explains the majority of the queuing latency. Okay. So you can actually go back to this application owner. Did you actually even know about this behavior? If you knew, let me explain why this is really bad. I'm going to now rate limit you, or maybe I'll have to shut you down, or and so on, right? Okay, so these 4 key ground questions, I think we can, as network owners now, ask any network solution vendors to come up with, techniques to address these 4 key questions. And there are a few attempts to solve these problems. And I'll share with you one such an attempt, which we call in-band network telemetry. There are a few other data plan telemetry solutions being proposed. But INT is essentially a read-only version of the Tiny Packet Programs paper, TPP paper published at CCOM a few years ago. Essentially, the idea is using the packets as log packets for themselves. Right? If you ask these high-performance devices for these telemetry features, they will say, good, those are all good to hear, but unfortunately, at the next generation, I have to deliver more packets at a higher speed, so I'm going to spend all my resources, engineering resources, physical resources, only to be able to deliver packets more fast. So that's why I said, okay, good. Then if you're going to focus on that, then let me just use packets as log packets, because you said that you can deliver packets very well. Okay, that's how this started. So when a packet arrives here at the first switch, it forwards the packet, but at the same time, it can add a lot of internal metadata information to the packet itself, like switch ID, arrival time, queuing delay, matched rules. Any of these pieces of information is available in the switch, irrespective of which switch you use. You just need to copy these things out so that you can harness this useful information for your network. So the second switch does that, third switch does that, and then when it arrives either at the last stop switch or last stop or destination end host or destination NIC, you can basically undo all the changes that are made here and then strip up this information and send the original packet up to the stack or applications, but you have collected this information successfully for every packet now. Okay, so this is already available, of course, on our solution. So I actually wanted to, try it out a few years ago. So this is one example. I just wanted to share with you this kind of cool chart because I was really excited about, to see this kind of chart now. So this is essentially queuing latency, and the unit here is nanosecond. This is time series, again, unit nanosecond. You can zoom in and in and in, so you can go actually at the nanosecond level, but this is actually 1 second here. So when the congestion starts, the queue blows up very quickly, and this is actually 1 millisecond now, right? And then if you take a snapshot or the queuing latency from every single packet going through this 25G port, you're going to just basically inundate your monitoring system. So you have to do some smart deduplication in the data plane directly. So the deduplication that I introduced here is basically some quantization. Every time I see the queuing latency swings across 256 microsecond range, then I create a report for that. So that's why you see this sort of quantization effect. So this gap is actually 256 microsecond. When I first saw this, actually this is not what I plotted. This is one of my colleagues plotted. When I first saw this, oh, this is interesting. This is really cool now because now for the first time in the history of networking, I can see this kind of chart from the real switch, hardware switch running at say 25G, 40G, 100G. Because so far, when we saw this kind of chart, it was all simulation. Now this is real, from real hardware, with real TCP. Okay? So that alone is very cool to me. But when I first saw this, I was wondering, okay, good, I can expect this kind of sort of quantization effect, but why are all the dips only going down here? Why don't I have some small upticks or large upticks? Okay? So then I asked another question. How many connections, how many TCP flows did you actually use for this? And then he said 5. Okay, now I understood why. Because we all know that when you have small number of TCP connections going through the congestion, they have global synchronization effect. And then global synchronization means that you actually have AIMD effect by TCP. So whenever they go up slightly cautiously, but when they come down, they do multiplicative decrease. So I was actually able to confirm this AIMD effect just by lowering that quantization value to, say, 16 microseconds. So this blue chart shows you that actually there is that AIMD going on. But if you look at a little larger scale, 256 microsecond latency quantization, you don't see that very well. You only see the dips. Okay? So this is cool. And then I asked him to actually increase the number of connections just to confirm that, yeah, as you have more connections, the global synchronization effect actually goes away. Okay? So confirming these kind of things at real time with real hardware switch is just so exciting. You can just now really do these kind of things. Right? So what does this mean? You can improve your distributed applications performance with this kind of telemetry data. If you're working on big data or machine learning fields, this is a new gold mine for you. You can actually apply your learnings and expertise to take advantage of this idea. And then I believe this is the first step towards self-driving network. You have to have this kind of fine-grained telemetry result to be able to eventually get there. So far, I've been presenting PISA as a packet processing machine. But essentially, what is packet processing? Of course, this machine has a humongous amount of I/O compared to CPU. But essentially, packet processing is just an event handling, right? So when a packet arrives, it's an event. You do some computation. You apply some computing and storage resources to that packet. And then the next packet arrives at the next clock cycle. And each event, you have limited physical budget, like, I don't know, maybe 400 nanoseconds, 300, some number of cycles dictated by the number of stages that you have in this machine. And then you have to finish processing this event, and then you have to send it out. So this guarantees amazing performance, extremely tight latency boundary, and essentially this becomes a real-time machine with some computing and some storage. Right? So if you consider this machine a real-time event processing machine, a lot of cool things can also happen. For example, people have started thinking about building DNS server using this machine, because if you receive hundreds of billions of DNS queries under DDoS attack, if you can say put maybe pin some hundreds of thousands of very popular queries, if you can directly respond to them directly from the switches, that's as fast as it can be. So at least those host names pinned in the switches are protected. Right? Key value caching. So you can actually use the on-chip SRAM, gigantic L1 cache available on this machine to host very popular key value entries and to improve your key value cluster's performance significantly. So I can talk about this as well. Key value replication done by this machine, and consensus acceleration and parameter service built with this kind of machines, or POPs-up services, lightweight POPs-up, right? So there are a lot of domain-specific, exciting technologies that can be sort of taken advantage here. But one common thing, despite the various, the wide scope here, one common theme is that once you can actually figure out the right way of offloading these ideas into this PISA machine, and once you are willing to sort of joint optimize your applications and these kind of machines, the performance gain is really, really amazing. We're really talking about more than an order of magnitude performance gain. So that's what is very attractive to the people who are actually working on this field. And then because this is realizable by this general purpose PISA machine, it doesn't necessarily mean that you have to fold these functions into the switches. You can actually come up with your own dedicated accelerators built with these kind of machines as well. Okay, so as a last example, let me just briefly talk about this key value cache or NetCache work and then conclude my talk. So this is the setup. You have a rack of, say, memcached servers or Redis servers hosted under a top-of-rack switch, and then your input workload arrives, gets and puts, and then typically these are sharded over multiple servers. You partition your key space, and you have this kind of varying workloads depending on which server you look at. Okay, but any real situation, you have highly skewed and rapidly changing workload. So your situation becomes something like this. For a few minutes, this server is highly utilized. For the next few minutes, this server is highly utilized because the popularity of these keys keep changing, and then the popularity is severely skewed. Okay? So in this kind of situation, how can you actually ensure a high aggregate throughput and also bound the tail latency at the same time? And why is this very hard? Because if you know that this is highly utilized and a lot of key value responses from this particular server is actually going into the tail portion, then maybe you can, at least as long as this is static, you can maybe repartition these, or at the cost of more complexity, you can actually maybe replicate these keys. But because this keeps changing, it's very hard to follow up on that approach, right? So you have to either compromise high throughput, or you have to either compromise tail latency. But how can you achieve both? So, right? So this is actually the evidence why it's very hard to achieve both. So if you have to set the particular tail latency, and if you have highly skewed distribution, so when you don't have any skewed distribution in key value popularity, your aggregate throughput is, say, more than 1 billion queries per second. But as this query gets skewed, your aggregate throughput goes down and significantly lower. Okay, so this is the problem that we're trying to address. And then here is the idea that we realized. So this is a typical top-of-rack switch, but it doesn't necessarily need to be, as I said, folded into top-of-rack switch. You can think of it as a separate sidekick of top-of-rack switch, or a special accelerator for the key value cluster. And and then obviously we're going to use this system as a cache, front-end cache for these storage servers. But there is one important non-goal here. We don't want to maximize the cache hit rate, unlike any other caches. That's not our goal, because our goal is just load balancing the workloads of these backend servers. So, and then there is a very interesting theory work published a few years ago saying that, hey, if you host the top n log n, or order of n log n items, where n is just the number of servers here, typically say 40 or 45, then you can achieve very good load balancing effect among these backend servers. Okay? So this is a really interesting and intriguing result theoretically. But unfortunately, it was very hard to build this kind of machine because this machine has to be damn fast. Because in the worst case, this machine can handle or must handle the same aggregate throughput as all these other servers. So if you have 45 servers, and then if you wanted to build this kind of machine using another server, there is no way you can achieve that. Right? But fortunately, with this programmable PISA kind of machines, you can actually enjoy this kind of theoretical results because this machine is damn fast. It's sort of storage challenging or storage challenged, but it can definitely host this kind of key value pairs, and it has enough flexibility to be able to parse these new protocols and then introduce some simple lookup logic. So what we did is we actually decided to fold it into the switch. So L2, L3 routing is not modified, and then we added this key value cache built with just on-chip SRAM. And then we also added this data plane query statistics logic built with some heavy hitter detector and so on, so that you can quickly tell the control plane that, hey, these are the new hot items, so you might probably want to replace not so hot items anymore with these new items and so on. Okay. So the result of this is very boring because once, as I said, once you feed it at the compile time, there is no runtime performance variation. Because it doesn't have a loop, it doesn't have a pointer, it doesn't have garbage collection. Right? So the performance is guaranteed across the value size of the keys, across the total cache size. And it's actually really billions of queries per second, which is an unheard of number as a single RU or 2 RU machine. Okay? But the benefit is not anymore boring, because remember this problem graph? As your key value popularity gets skewed, we actually gets even better because the servers are fully utilized. So this blue portion is what is handled by the spec-end servers. And in addition to that, the switch or the NetCache can actually directly handle a lot of popular queries. So this is a really interesting result because when the existing solutions work worse, this solution actually works even better. And then that the factor of betterness is actually orders of magnitude. So this is the kind of cool idea that I wanted to share with you. So summing it up, so why I believe that data plane programming is going to be here and then stay, because you can develop your new features, your beautiful ideas very quickly. You can reduce your network complexity. If programming doesn't necessarily mean that you introduce more things. You may actually want to remove things that you don't need to use, right? So that's simplification. And that simplification allows you to use your hardware resources more efficiently. And you can get better visibility because you know exactly what you need from your network, and then you can program that specific logic in the data plane. You can enjoy modularity. You can also enjoy portability, meaning that you write your P4 program as more P4 programmable devices arrive across generations, across vendors. You can keep reusing your P4 programs, so you can essentially ensure silicon independence. And then finally, you can own your own beautiful ideas, right? So that's why luminaries like Ben Horowitz says that, yeah, protocols are gone now. It's all software. So this is the last slide. So some observations. So there are a lot of interesting things that can happen here, but other than those beautiful ideas, as a researcher, if I wear more like academic hats, why is this data plane programmability so exciting? That's because finally, as a networking people, or one of the members in the networking community, we now have our own machine. So far, we had a lot of fast chips, but they happen to build some protocols at the high speed. As I said, it was a great engineering achievement, but at the same time, great engineering artifact. We didn't really learn from the other theories and disciplines of the computer science. We didn't try to define our own machine. Now we have that machine, and we have that programming model, we have that abstraction, so that excites me a lot. And we can actually learn from a lot of other subfields in computer science. Every day I learn, whenever I interact with language people or compiler people, machine architecture people or theory people, I realize that there are some things that they have done in the past 30 years, 40 years, are now re-applicable to this new machine. Okay? So that's also very cool. And of course, it's super fun to try to figure out your new beautiful ideas, and then try to also explore the fundamental limitations and upper bounds and lower bounds of these machines. So yeah, so let me conclude my talk with this. Thank you.
Thank you.